Okay, that's clear. Yeah, we can get started. Yeah.
Okay, so thank you, Ambedkar, and well, the organizers of this workshop. It's very nice. So I guess my talk is going to be very different than the previous talk, at least. But the emphasis is going to be more on these aspects of sequential decision making. So it's not, I don't work on reinforcement learning, and this talk is not really about machine learning, but there's this sequential aspect that I think could be interesting. And it's based on the joint work with a former PhD student, Ervin Tánczos. Okay, and the question we're asking, well, there's this kind of slightly silly cartoon is, well, how hard is to find needles in a moving haystack? Okay? So there's many situations where you might want to detect a signal that is changing as it's being measured, right? So you are measuring something, a system, and the system is changing while you're measuring. You cannot keep up, right? So a prototypical example comes more from, well, communications, like detecting covert communication. If there's maybe some malicious activity, someone trying to send information through different channels of communication and switches channels as they go to avoid being detected. Or maybe a bit more relevant nowadays, right? You want to detect hotspots of a certain disease, right? But you cannot measure everywhere at the same time, and so on. And the fundamental question, its talk is going to be really focused more on the fundamental questions of difficulty of these inference problems. Is okay, how hard is it to see a moving target? Okay. And there's quite a lot of related problems, some coming from information theory, communication theory, some coming more from signal processing, from statistics. The setting we are going to consider here is a little bit different. Okay, so just to have a bit of a graphical motivation, right? So imagine you have a network, could be a physical network, so different cities, and maybe there's, well, two individuals that are, let's say, malicious or something like that, and they move around, right? So at time 1 they are here, time 2 they are still there, but at time 3 the individual that was at this node in the network moved to this node, and so on, right? And they just kind of circulate around, and you like to, well, try to detect them to see if there's anyone up to no good, right? But unfortunately we don't have access to all this information. So what is shaded here is stuff you don't see, and all you can do at any time is just measure one of the entries in this network, right? So at time 1, maybe you measure this one, and you have maybe a noisy perception of what's going on there. And then maybe at time 2 you measure this, and you have a noisy perception of what's going there, and, well, you see that, well, maybe there's someone malicious there, but I cannot be sure. I cannot put my finger on it yet. So let me maybe measure it again, and, well, this measurement seems to reinforce my belief that there's something going on, and maybe measure again, and then in the meantime this individual move somewhere, so I get a measurement that's maybe not so reinforcing of the fact that there was something malicious. So maybe I have to eventually start measuring somewhere, right? So what I would like to do is figure out, okay, how can we do this effectively, and how difficult is the problem? How strong does sort of your signal need to be? How informative do these measurements need to be in order to be able to detect something? So let's try to formalize this. Okay. So I'm going to be interested in so-called sparse signals, right? And for me, a signal is just a vector of length n. You should think of n as being very large, 1 million, something like that. And it's a sparse vector, and it can change over time. So there's a depends on time, and time is discrete for the purposes of this talk. So time 1, 2, 3, so on. So and the signal is essentially the components. The various components in this vector are mostly zeros. There's a few of them that are not zero, and take the value mu greater than 0. Okay. So S of t is the signal support at time t. Right, is what are the entries of this vector that are non-zero? Okay. So this can model, for instance, the activity level in channel I at time t, or the amount of anomalous traffic level in a network, node I at time t, and so on. And just in terms of lingo, right, the signal components in S of t are called sort of active. They are present there, right? And the active components in this model have all magnitude mu, right? It's possible to consider arbitrary signs and different magnitudes as well, but that just complicates the presentation a lot. And in a sense, in a minimax sense, this setting is sort of the worst case setting. And we are interested in sparse signals. So you should think of the size of the support as being much smaller than n. Okay. Good. So these are the sort of the objects I'm interested in detecting. Let's discuss what can I measure about these signals, right? So it's going to be a very simple, again, very simple model, right? We have, let's say, a budget of m measurements, m noisy coordinate-wise measurements. And so at time t, we can choose, well, to take a measurement of component at of the vector. So I choose to measure, for example, entry 42 of the vector, right? And I observe the value of that entry plus some noise. And noise here is just going to be a standard normal, just again, to make life a little bit easier. Some of these things can be generalized, but let's keep it as simple as possible. Okay, so at any time, I can essentially measure one entry of the vector and I get a corrupted measurement, right? That's as simple as that, but this already has a lot of flexibility. So that's where sort of the adaptive aspect of this problem comes in. So I can have a paradigm, a sensing paradigm that's adaptive sensing, where I can choose the location of the measurement based on all the past observations, right? So there's a sequential nature of the observations, right? I have observations and a design essentially up to time t-1, and based on that information, I can decide where to collect the next observation, right? And this is a very powerful setting. And well, as a sort of, as a counterpart of that, there's also non-adaptive sensing, where I still have a lot of flexibility. I can choose where to put my measurements, but I need to do this before I get any observations. So I have to decide before I even look at any data, where am I going to put these measurements? And all these designs can be random, can involve randomization. That's not an issue. Okay. So essentially, adaptive sensing allows to use the past observations to kind of guide the sensing process, right? To find reinforcing information to help us make a decision about a certain inference problem. Okay, and of course, non-adaptive sensing is those paradigms are a subset of adaptive sensing. Good. So now we have, I already said, well, there's a certain signal that I'm interested in. This is what I can measure. I haven't told you what type of problem I'm looking at. Okay, what is my inference goal? Okay, and the goal we are going to focus on is the simplest statistical question you can ask, right? Is as simple as, can we see if there's something there or not? I'm not trying to estimate a signal to locate these anomalous components. I'm simply trying to see if there are any anomalous components or not. Okay. So the null hypothesis here, well, is just that, well, signal support at time t is equal to the empty set for all times. So essentially, there's nothing there, right? There's nothing to be seen. And the alternative is that there is a signal support set. It's not empty, right? And I would like to determine this. So I would like to decide between these two hypotheses. And so my decision is going to be a binary decision. So I just have to construct a binary function, right? That takes, well, my design, the set of ATs and Y of T's, right? And maps it to 0 or 1, right? Where 0 would correspond to the null hypothesis, H0, and 1 would correspond to H1. Okay. And I would like to do this in a way that I make, well, I have a small probability of error, right? So what are the two errors we can make here? Well, can have a false alarm, essentially say that there is some signal there when there's some active components and there are not. So probably it's the probability of your function taking the value 1 when you are actually under H0, right? Or probability of missing, right? Not seeing a signal when it's there. Okay. And my risk is just going to be the maximum of these two. So I want both errors to be small. Okay. Good. So I hope everything is clear up to this point. If not, please let me know. I cannot see if there's anything in the chat. No, there's nothing. So so at this point, so we have sort of the entire setting, but I haven't told you what the signals I have look like, right? So essentially, I didn't describe the alternative yet. So but before doing that, let's even just look at a simple case where suppose there's no dynamics, the signals are static. What can be said? Okay. Well, so essentially, the signal support doesn't change over time. So what is known for this problem, and this has been looked at by different people with different levels of granularity. Sometimes you want to characterize really sharply a phase transition. Sometimes you just want to get a cruder understanding, right? So the first thing that comes to mind if you are thinking of non-adaptive sensing is, well, let's say my budget of measurements is actually equal to the signal length, so I can measure each entry exactly once. This is what I would call uniform sensing, right? Then if you want the risk, the probability of making an error to be smaller than epsilon, what are the necessary conditions for your signal magnitude to be? How strong does your signal need to be? And this result, this comes from Adari and co-authors, tells you precisely this. It's the lower bound telling you that signals below this are not detectable. Right? And maybe it's easier to look at this without so many formulas here. And if the size of support that I call lowercase s is smaller than square root of n, then signal magnitude needs to be larger than square root of log n over s squared. Otherwise, you cannot detect a signal. What happens if you try to do adaptive sensing? Well, then you get a very, very different result. Surprisingly, maybe too different, right? If you want the risk to be smaller than epsilon, then the signal magnitude, it's suffices for the signal magnitude to be larger than, well, square root of 2n over sm. M is the number of measurements times log of 1 over epsilon. So if m is equal to n, this is like square root of 2 over s. Okay, so even if the size of the support set is growing with n, if you're scaling it up with n, you can detect increasingly small, weaker signals, right? So it's an enormous difference. Let's see if this comparison is fair, but let's save that for the next slide. But there is this is a lower bound, but you can achieve this lower bound. There's a procedure that allows you to do this. And maybe a more interesting question is that, well, right now I'm just characterizing the support in terms of their sparsity, but there might be structural assumptions. Maybe all the active components are clustered around in a certain region or something like that. So when you have structural assumptions in terms of uniform sensing, the picture can change a lot. And this paper of Adari and co-authors is really dedicated to studying what different combinatorial or geometric assumptions on support sets can mean for the difficulty of this problem. But interestingly enough, when you are in this realm of adaptive sensing, you cannot really capitalize on structural assumptions, right? This is the result you'll get even if you have a lot of structure. This lower bound is valid even if you have a lot of structure, which is maybe remarkable that structure doesn't really help. Is this comparison fair? Well, strictly speaking, it's not, because uniform sensing is maybe not a very good idea if you're thinking on non-adaptive sensing. A better thing to do, right, and if you scribble it a little bit, you'll see it quickly, right, is instead of measuring everywhere, well, you measure instead a few coordinates, but you measure them more than once. So you get a higher signal to noise ratio in the few coordinates that you measure. So if you do this, right, you'll get a result, and this is still non-adaptive, right? You decide where to measure beforehand, but you'll get a lower bound for the signal magnitude that is essentially, and the price to pay for being non-adaptive is in this logarithmic term, this factor log n over s, which can be very substantial, right? Because if n is 1,000,000 and s is a few hundred, this is quite a big constant. Okay. So let's see. I think I skipped here something that I shouldn't have skipped, but okay, no, everything is here. Sorry about that. So this was the static case. Let's move towards dynamics, right? So let's think of a, well, probably try to think of the simplest stochastic model for signal support evolution over time, right? Something that we can try to study here, right? And it's going to be a very, very basic type of model, right? So at time one, I just pick the active, locate the active components uniformly at random over the place where I can put them. So in this vector, this column vector, it has n slots, and I just put the S active components uniformly at random there. Okay, so this is what I have at time one. So now how do I evolve this signal over time? Well, what I'm going to do is, it's in a sense, it's kind of a lazy random walk, right? For each active component, I'm just going to flip a coin. And I'm going to flip a coin with probability P. Sorry, there's something missing here in this slide. With probability P, right? And the coin flips heads with probability P and tails with probability 1 minus P. If the coin flips heads, that component is going to move somewhere else in the next step. Otherwise, if it flips tails, it's going to stay. So in this case, the ones that flip green here are going to stay. So at time two, you will stay at the same place. And the ones that flip heads in red, they're just going to move to some other place. So essentially, I end up at time two with a support set that has exactly the same cardinality, right? But it's slightly different. And then I do the same thing again and again and again. Right. So in this case, only one component changed. Okay. So it's a very simple model for signal evolution, right? And it's just formalized here, but don't read the top part of the slide. This parameter P, right, this coin flip parameter, is essentially controlling the rate of change. So if P is equal to 0, I will never change a component, so I have a static signal. If P equals to 1, well, essentially at every time I have a random realization of a different support set, right? And in between, I have a sort of continuum of this. So just to have a bit of an idea of what this looks like, let's take a small value of n. So n is 50 and s is 5. And in this picture, the horizontal axis represents time, and these are the signal components. So here is P is equal to 0.2. So what you see is that, well, there's these 5 components, they stay put for a bit, and then at some point, some of them start changing, right, and jump to some other place, and so on, right? And actually, just by construction, the amount of time a component stays in one place is geometrically distributed with the parameter P. So on average here, the average length of these lines is essentially 5. So if P is larger, of course, the signal changes much faster, right? So things get more garbled very quickly, and even faster if P is larger. Okay, good. So now we are sort of set to try to formalize a question, right? Which is this hypothesis test. We like to test if the signal, the support set is empty, right? So there's no signal there, or you have a signal with the dynamics described earlier. And the question that we want to ask is, okay, how large is the signal strength, mu, right? How strong does your signal need to be, right? How mu is just the signal to noise ratio of your measurements, right? How strong does your signal need to be to ensure that the risk is smaller than some value epsilon, right? And epsilon is just, you can fix it, 0.5 or 0.05 or whatever, epsilon, okay? And because now we introduce so many things, it's good to maybe recap a little bit, right? So we'd like to know what the signal strength should be, right, mu, as a function of, well, epsilon, right, your target risk, the signal dimension n, the sparsity, the number of active components, the speed of change of the signal, and the total number of measurements. Good. Are there any questions at this point?
Please go ahead, Ervin.
No? Okay. Oh, it's just good to know if there's any clarification needed. Okay, good. So maybe one thing that one can realize now is that, well, if the number of measurements is very small, right, there's no hope of getting this, no matter what, right? Because you only get evidence of a signal if you hit an active component, right? So if you take just very few measurements, right, you won't hit a signal component with high probability. And so you won't be able to do anything, right? So if you take essentially on the order of, well, less than n over s measurements, right? Regardless of what you do, right, the probability of not hitting an active component will be at least given by this expression here, right, which is easily bounded by what's there on the right. And you see that this is bounded away from 0. So you cannot get an arbitrary value of a risk with an arbitrary value of epsilon. Okay. So the number of measurements must be at least as large as some value proportional to n over s, or that proportional constant might depend on epsilon. So if you want a really small error, right, you have to make that constant large. Right. So this is the bare minimum number of measurements you have to make. And this is what we call the small sample regime. And the focus of this talk is going to be primarily on this regime, right? And arguably, this is the most interesting regime, right? Because it's the regime you want to be in if you want to detect signals quickly, right? You want to find the hotspot of a disease, that there is a disease propagating quickly. You don't want to just keep sampling. Okay. Good. So how do we go about this? Well, now it's going to be maybe more algorithmic. Let's try to come up with an algorithm to solve this problem. Okay. So what is our observation model, right? You just choose where to measure. That's your A sub t, right? And you get a measurement that's, well, either normal mu1 if you hit the signal, or 0,1 if you don't hit it. Okay. So let's suppose first, very, very simple, that there was no observation noise. So if you measure a component, you just get the value of that component. Well, then it's very clear what you want to do, right? All you have to do is keep sampling around until you hit an active component, right? So maybe you take a measurement here. So again, time here is in the horizontal axis, components are in the vertical axis. Take a measurement here. You didn't see a signal. Let me take a measurement somewhere else. I didn't see a signal, and so on, and so on. And now I measured a signal component. I'm done. I know there's a signal there. I can go for the alternative hypothesis. I know there's active components. Okay. So if there was no noise, problem would be very easy. So how do we go about doing this if there's noise? Well, here's a simple idea. Well, essentially, yeah, you're done if you hit an active component, right? And if you exhaust your budget of measurements and you don't hit anything, you just say there's no signal. So how do you go about dealing with this if there is noise? Well, here's a very simple idea. Let's just take this noiseless procedure and replace these measurements. Let me call them queries now, right? These queries by essentially a sequence of measurements at some component, a sequential testing procedure, right? Very akin to Walt's sequential likelihood ratio test. So what we're going to do, right, is, let's see, I don't have an illustration here yet. So you're just going to replace, you say, okay, now I'm going to focus on entry 42, right? And I'm going to start measuring there, and I measure it for a number of times in a clever way until I can make a decision with enough accuracy if there's something there or not. Okay, so each selected signal component, each query, right, measures the same component repeatedly to determine if it was active or not, right? And what is the difficulty here is that, well, a signal might be there when you start measuring, but then it's gone, right? So you want to get guarantees even in that case. Okay. So algorithmically, what are you going to do? right? You have a certain number of queries, let's call it T, right? I'm just going to a priori decide that I'm going to just choose core components uniformly at random that I'm going to query. And for each one of these components, I'm going to perform this, this sequential testing procedure, this sequential threshold test. And then, well, if this test returns signal, then I'm done. I say, okay, there's something there. Otherwise, I just continue until the budget is exhausted. Right? So graphically, it looks like this. Maybe I decided to start at component 10. I took a measurement. There was not enough evidence there to still make a decision. So I take another measurement and I take another measurement. And now at this point, I decide, okay, I'm pretty sure there's no signal. Let me go somewhere else. And I do the same thing. And same thing again. And maybe here, now I measured this component. I measured again. I start kind of reinforcing evidence that there might be a signal there. Well, the signal is gone there, but I got another measurement, and maybe even after that measurement, I can be sure that there is a signal there. Okay, so essentially this sequential thresholding test, maybe it looks a little bit convoluted here, but you're just collecting multiple measurements at the same component, you are averaging them out, and then you're comparing them to thresholds. So if this average is above a certain threshold, you declare signal, and that threshold changes with where you are in this procedure. If it's below a certain threshold, you declare there's no signal. Okay. So that's a methodology, right? And of course, the devil is in the details. So this sequential thresholding test, right? You have to calibrate, you have to determine these thresholds very carefully, right? But what you can guarantee, and this is the important part of the slide, is, well, if you're under the null, right? If you are not measuring any signal, then this testing procedure will wrongly declare that there is a signal with probability at most epsilon over t, right? So the probability of essentially giving a false alarm is epsilon over t. And this is the juice of it, right? If the first j measurements, right, are of a signal, then and if the signal is strong enough, it's stronger than this, where you see j appearing there as well, well, then this testing procedure makes an error, declares no signal with probability at most epsilon over 3. So essentially, you give guarantees that also are valid even if the signal changes over time there. So that's sort of the key machinery that we need, right? Because then you put this together with the other approach and you easily can show what the performance is, right? And then you get a result that's kind of like this, again, stated here in painful detail. And the result is not asymptotic, although here the way it's stated might look a little bit more asymptotic. But what I'm saying is that, well, if I have this many measurements, so on the order of n over s with a factor that depends on epsilon, and if I want the risk to be small by using this procedure, so the probability of making an error to be smaller than epsilon, then signal magnitude needs to be larger than this quantity. And this is maybe a bit harder to read, but if the rate of change p, that I even allow to change with n here, if the rate of change p of the signal is not too small, what this says is that the signal strength needs to scale like square root of 4p, the rate of change, log n over s. Okay, and this is sufficient for signal detection. Okay. So that's the main message of this this procedure, right? I'm not saying this is optimal at this point, right? But this is what you can show, and you see clearly the effect of the dynamics playing a role. Like if p is small, the signal is almost static, right? This term will be small, and actually that term is going to dominate. If p is large, then this term is going to dominate, right? And I have a opera singer living next to me, so if you hear some opera singing, is my neighbor. She is practicing. So if the rate of change is really small, right, essentially you're back in the static case. And there we know that in this small sample regime, a constant signal magnitude suffices for adaptive sensing. Right? If the signal is changing really fast, if P is equal to 1, essentially there's nothing you can do with adaptive sensing because the signal changes. It's independent at every snapshot you look at. So this problem kind of boils down to the sparse mixture testing problem that has been studied very carefully, in particular by Judy Inkster and Donahoe and Jin. Right? And there, well, you know what are the sort of sufficient and necessary conditions, and it's exactly what we get here, right? So we are doing something right in these extremes, and what's happening in the middle also seems to make some sense. Okay, and this remark I don't want to talk about, but the proof of this result, right? It's not complicated. It's just putting everything together. It's bookkeeping, it's accounting, right? It's just tail bounds and unions of events. Nothing, no technical heavy machinery. Okay. So the summary so far is that in this small sample regime, right? If you want the risk to be small, well, there is a procedure that allows you to guarantee this if the signal magnitude is large enough. And what does that mean? Well, if the signal is static, signal magnitude needs just to be above a constant. If the signal is dynamic, it needs to scale like square root of P log n over S. Okay, so I see there's something in the chat. Now, let's see. Yeah, precisely. So Chernoff-Hoffling bounds, essentially tail bounds, and that's it. You can't possibly extend this to be able to sense multiple signals at a time. We didn't consider that. We consider this sort of prototypical example because it's somewhat the easiest to do. But I don't see necessarily a problem of considering that in terms of an algorithm to show lower bounds, as we are going to discuss now. That can make things challenging. Good. Okay. So actually, the question was a good place to piggyback on this, right? So these aren't just sufficient conditions. Can we show something about necessary conditions? And for that, let's focus first on the non-adaptive sensing regime. Let's see. So now we are not thinking about a specific algorithm, but okay, what is necessary for a test to have small risk? Okay. So if you don't allow adaptive sensing, so if you're thinking of non-adaptive sensing, right, you have to select your measuring strategy, well, before seeing any data, right? You cannot adapt to the data, right? And then what you can show, again, this is not an asymptotic result, right, is if this type of condition, so if you want to test with small risk, right, risk epsilon, then necessarily signal magnitude needs to be larger than this in the case of a static signal, if P is equal to 0, if signal doesn't change. And if P is equal to 1, it scales like this. Right, and this holds not only in the small sample regime, but in all regimes. These are just lower bounds, right? So you'll get this rate, and that rate is actually different than what's in this classical work by Inkster and Suslina, just because we are not considering uniform sensing, but you still have quite a lot of flexibility in constructing your sensing strategy. But in the small sample regime, right, what you see is that you'll get essentially the same scalings. There's a slight difference between these two bounds, but it's very minimal, right? So essentially it's saying that, well, either for static signals or very lively dynamic signals, the difficulty of the problem in terms of signal strength is about the same. And the lower bound for P equals 0 is likely to be loose, and this can be seen by going through the proof. So what it means, right, is that, well, these are the two extreme cases, and it seems that nothing can be the dynamics don't help at all in the small sample regime. So what happens in between? It would be hard to believe that that something else would happen in between, right? It's still a question, right? So we can formalize this intuition when there's only one active signal component. So when S is equal to 1, right? We can show that, well, you cannot do better than for static signals. It's not so easy to formalize this intuition when S is greater than 1, unfortunately. But the two extremes should give essentially the all that you should have, right? So the picture that we have now, right, and this is the non-adaptive sensing case, right, is that we have these bounds for the static case. For the dynamic case, everything matches nicely. Here we don't know, but it should be something between these two, which means there's not much you can do with dynamics. So here you see a tremendous difference in terms of the ability of adaptive sensing to kind of be able to use the dynamics, the knowledge of the dynamics and this dynamic behavior to their advantage, to chase this moving target. Okay. Good, so let's see, in terms of time, we are doing well. How do you show these lower bounds? So maybe it's a bit more didactical. Right? So the idea is an idea that is kind of sort of standard in trying to get lower bounds for hypothesis testing, right? Which is to look at the risk as essentially using Neiman-Pearson's lemma, right? Relate the risk to the best test you can consider, which should be a likelihood ratio test, right? So essentially you just write or lower bound in this case, this worst case risk by this expression where L here is the likelihood ratio, essentially the ratio between this, in this case, probability mass functions of the observation, probability density functions of the observations under the alternative model and under the null model, right? And this is nice because, well, all you have to do is study this expectation. It's not an easy expectation to study because we have an absolute value there, but we know Jensen's inequality or Cauchy-Schwarz, right? And we can just apply Cauchy-Schwarz here, right? And essentially relate the behavior of this thing to the behavior of the variance, right? Because the expected value of the likelihood ratio is actually 1, right? So to get a lower bound, you just have to study the variance of this quantity, okay? Unfortunately, this doesn't cut it. It doesn't cut it because there's quite a lot of slack going from here to here. And it's because the distribution of the likelihood ratio is rather heavy-tailed. So this makes this approach, it's still valid, but you'll get very weak lower bounds, so not very interesting ones, right? And let's maybe not discuss this in detail because it gets a little bit technical. The important thing, essentially what happens is that there are certain designs that on one hand, on average, they don't hit the active components very often, but when they do, they hit it a lot of times. So those designs don't concentrate, the average of the number of times you hit an active component doesn't concentrate well around the mean. And that's what causes all the problems here because you have this exponential term there. So what you do, you sort of truncate this likelihood, you kind of you tame the tails, you remove a little bit from it, and then you can now bound this nicely by this expression, and you trade off a little bit of error, right, in this truncation by something that behaves better in terms of second moment. So if you're a probabilist, you would call this the second moment method, and it's a second moment method with truncation. And it's also a common technique used in probability. Good. So this was just a technical remark about the proof. What happens in case of adaptive sensing? So there the story becomes more complicated, of course, right? So we know what happens if signals are static, right? We know that signal magnitude needs to scale like this, and in small sample regime, we get just that the signals need to be larger than a constant, right? In the other extreme, we also know, because the dynamics, all the signal realizations are independent from each other. So we are in the sparse mixture case, no matter what. So dynamics don't do anything, right? So in between, what happens? Well, that required a little bit more work, right? But we could say something, and we focused on the case of one active component for technical reasons. It's possible to lift this, but it becomes rather complicated, right? So these are lower bounds again. So if you want the risk to be smaller than epsilon, what you know is that the signal magnitude needs to satisfy these two conditions, right? This is just what it comes from the static signal condition, and this is what comes when the signal is dynamic. And it's maybe a bit harder to read, but you see exactly where the right quantities are. You have P there appearing there, right? And you have a log of essentially M here. So, and I don't know why Zoom is doing some weird things on my side. I don't think you can see it, right? So now we have a bit of a better picture, right? So in the small sample regime, if we want the signals to be detectable with some risk smaller than epsilon, probability of error smaller than epsilon, so now we have sufficient and necessary conditions, right? At least in the case S equals 1, right? And you see that everything here matches. The only thing that maybe doesn't match here is this P square inside there, which is actually it should be inside the log, right? So we are not doing as well here, right? And if you have the case S greater than 1, while the extremes are easy, what happens in between, right? I conjecture this is going to be what the bound looks like, but it's just an informed guess rather than a solid theoretical statement. Okay? So good. So again, how do you go about showing such results? It's still a truncated second moment method, but now you have to deal with the fact that the signal is dynamic, and that causes some difficulties. And that's why we looked at the case S equals 1, because what happens is that the signal stays at a place for a geometric amount of time, and then it moves. So essentially, you can decouple what happens in different windows of time. And these windows have random lengths, but you can decouple what happens in those times. And our proof crucially relies on that. And that's why it's difficult to generalize it for the case S greater than 1, where you don't have this decoupling so explicit. Okay. I think it's possible to generalize this to the case S greater than 1, but it's not obvious what's the best way to do it, right? A simpler problem would be to have, in a sense, just a concatenation of S1 sparse signals in dimension n. So if you formalize this heuristic, then you should be able to get a lower bound. But it's not, at least we could not find a good way of doing this. Okay, so this is the full picture now. So now we, what's happening here, what is the role of dynamics in this small sample regime, and the fact that adaptive sensing can really capitalize on the dynamics, while non-adaptive sensing is really oblivious, cannot do it, right? If you consider beyond the small sample regime, if you are in an arbitrary sample size setting, the picture becomes much more complicated, and we don't have good answers, right? We do have lower bounds that hold. We don't have procedures that deal with this, and the reason for that, right? So in particular, we don't have anything to put there, is that our method is very naive and myopic. The algorithm I described, right? You sample at a point at a certain place, and if you don't find any evidence, you just kind of forget about anything you've done, and you just go to some other place, right? But if you have a lot of samples, you want to use knowledge that was acquired over time and kind of put it together, right? So you don't want to just naively ignore all that knowledge. That's why it's not so easy to look at what happens there. And this is why if you have a lot of measurements, you can do actually much better. And this is just a method based on averaging the observations you get. And in the non-adaptive sensing, I think the story becomes much more complicated, right? Because you will be able to capitalize on the dynamics, right? Now, there's a big difference between what happens there and what happens here. And what happens here should kind of interpolate between these two cases. Okay, so it's an interesting setting to look at. It's not entirely obvious how to do it. Okay. So we did a bit of a numerical evaluation of this just to make sure that we were not completely off the mark, right? Because it's in a sense a very theoretical work, right? So what I'm representing here in the horizontal axis is the signal strength. You can think of mu, but it's just parameterized by in this way, so that at least asymptotically the transition should happen at that point for adaptive sensing. So at this point t equals 1. And what I'm representing here is, well, it's essentially the risk. It's the type 2 error because this is all under the alternative, but it's essentially, you can think of it as the risk. And you see that there's quite a dramatic gain in this case. So it's n equals to 2 to the power 15 and s is just 2 to the power 4. And this is a very static signal, p equals 0.2, right? You see that you can gain a lot by using an adaptive sensing procedure. And this is, in some sense, an oracle procedure for a non-adaptive setting. And as the signal gets more agitated, this gap starts getting smaller, right? It starts getting a little bit harder to capitalize on the adaptive sensing. Good. So actually, I will end earlier, which is good. What are possible extensions or sort of directions for the future? Well, this large sample regime, I think, is very interesting. It's all clear what is the best way to design an adaptive sensing test, right? And what is the optimal, even a non-adaptive sensing design is not clear. What is the optimal way to do this? And what's the effect of the dynamics in the problem difficulty? And the method I described was adaptive to P, right? You don't need to know the signal dynamics and you adapt to it. So in this case, it's not clear what you can do. Maybe a more interesting setting that we are starting to explore a little bit is when you look at more restrictive signal dynamics. Because right now, what you have is essentially a signal that's moving in a complete graph. But that's not how most dynamic signals work, right? So if you think of a signal in a network, right, you have, for example, a network of cities or something like that, and you cannot move from one extreme to the other very quickly, right? You have to go through all these cities, right? So this would be useful to deal with, for example, epidemic models in a network where you are trying to detect like hotspots of a disease, or maybe a simpler setting, activations might be clustered together. They might not be moving around in a completely independent way. Right? Of course, this makes the problem much more interesting, but much more difficult, right? And you can think of relatively simple settings as the signal propagates in a lattice or something like that. And the last one is maybe not so interesting for this community necessarily, but there might be situations where your measurements are not only affected. It's not only the mean of the measurement that's affected, but the variance is also affected, and that can be very useful to the, especially if the variance is also enhanced, is increased. And this SCT algorithm that I described can deal easily with that situation. So this is what I wanted to say, right? It's always odd to give this online talks because you don't see the audience, right? And this is all based on work that was done with Ervin Tánczos, right? And it's appeared in Bernoulli. There's also an archived version that is essentially the same paper. And this is not very recent work. I told Ambedkar for this conference, I think this would be the best fit, but I hope you got something out of it. Thanks.